Hi everyone, in this video we solve example 1.1 from the book Applied Thermodynamic Mechanics and Telescopes. Here is the statements. Unit mass of a fluid at a pressures of 3 bar and with specific volume of 0.18 meter cube per kg contained in a cylinder behind a piston expand reversibly to a pressures of 0.6 bar according to a law P is equal to C by V square, where C is constant. Calculate the work done during this process. This is the diagram of the statements. This is the piston. Behind this piston there is a fluid that have pressure P. So this pressures of the fluid P pushes this cylinders and it give you the work output Q, and in the same way the pressures of the fluid decreases. The pressures P1, that is 3 bar, and after expansion the pressure P2 you will observe that is 0.6 bar. Specific volume V1, that is given 0.18 meter cube per kg. Expansions taken place by the law, that is P is equal to C by V square, where C is constant and V is the specific volume. So if I draw the PV diagrams, it is very simple. So this is this side, this is pressure, there is specific volume. So at initial state the pressure is very high, at final state there is this is P2, the pressure is low. So expansion is taken place by the law, that is C by V square. So this is, let's say, 1 and this is P. The volume here is specific volume here is V1 and the specific volume is V2. So we need to find the work done by this process. So the work done is equal to minus M integrations from 1 to 2 pressures and change in volume. So mass is equal to unit, so we will consider this mass as a 1. This pressure is given in terms of C by V square, so we can write minus 1 to 2 pressure C by V square. So this is C is constant, so I can write minus C, and V square, so I can this is 1 over V square, so I can say V minus 2 dV integration 1 to 2. Now the integration of the specific volume minus 2 is very simple. Just add plus 2 with it and divide with the same exponent minus 2 plus 1, and it will be the integrations of this. So you can say W is equal to minus C and then apply the integrations. So its integrations will be equal to V minus 1, and minus 2 plus 1 is minus integration 1 to 2. Then now that apply the limits after that, so work done. So this minus minus become plus C, so you will get 1 over V 1 to 2, then apply integrations C, and it is 1 over V2 minus 1 over V1. So let's say it's equation A. So here is some terms that is unknown. It is V2, V1 is known, C, so C is equal to P is equal to C by V square. So this is P1, this is V1. Then you can find the C value, that is P V1 square. So what is P1? That is P bar multiplied by V1, that is 0.18 square. So after simplifications you will get its value of the C, that is 0.0972 bar meter cube per kg square. And then V2, so I can write this equation in terms of the substitute P2 C divided by V2 square. Now the C value is constant. We need to find the specific volume V2, and for simplifications for V2, we can write this as V2 is equal to V2 square, that is equal to C divided by P. Further, take it under root. This V2 value will be equal to under the root C. What is the C? That is constant. It is 0.0972 divided by P2. What is P2? That is 0.6. It is given in the statement. I already mentioned at the start. So the simplifications, you will get the specific volume value, that is 0.402 meter cube per kg. Now put all these values in this equations. C value has been determined, V2, V1, or the work done by the systems. You will get that is, what is C value? That is 0.0972 into 1 divided by what is V2, that is 0.402 minus 1 divided by V1, that is 0.18. After simplifications on calculators, you will get work done by the system, that is equal to minus 29,840 Newton meter per kg, because the mass is 1. So this is the work done by the systems. You will observe when the fluid temperature drops from P1 to P2. I hope you understand. If you still have any confusion, you can ask. Thank you so much.